He has made pivotal contributions to the phenomenal increase in the power conversion efficiency from less than 4% to more than 25% within the last decade, and to the dramatic improvement of their operational stability. Today's prevalent and most efficient perovskite solar cells embodiments borrow their design concept and choice of components from Graetzel's solid-state version of dye-sensitized solar cells. Professor Graetzel has received numerous prestigious awards, including the Rank Prize in Optoelectronics, Materials Today Innovation Award in the USA, Albert Einstein World Award of Science, Millennium Technology Prize, Faraday Medal of the British Royal Society, and the Global Energy Prize. He has received 12 honorary doctor's degrees and has been elected member of many academic memberships and fellowships, such as the Royal Society of Chemistry and the Royal Society. He is author of over 1,800 publications, 2 books, and inventor-conventor of over 80 patents. His work has been cited almost 500,000 times. His H index is almost 300. According to the Web of Science in 2022, he's currently the most highly cited chemist in the world. After his presentation, we'll have questions and a panel discussion. So if you are online, please write down your questions on the chat. And if you are here, just ask for the microphone. The title of his presentation is Molecular Photovoltaics and the Rise of Perovskite Solar Cells. Thank you very much, Professor Graetzel. The floor is yours.
Thank you, Sava. It's a pleasure to be here, an honor, and I'd like also to thank Omar for his kind invitation. And yeah, our work is in the field of solar photovoltaics. However, we also work on solar fuels. And for some time, we worked on lithium-ion batteries, the best copy concept application for lithium-ion batteries. And so you can find more details on our studies here outside our website. The lecture itself will be focusing on photovoltaics. And we use photovoltaics, of course, to make solar fuels. We also do photoelectrochemical studies where we excite semiconductor and produce the fuels directly from that excitation. However, that will have to be discussed in one of these next periods. So there's 30 minutes now. Bear with me, we'll be on photovoltaics. And so, yeah, so the way our journey went was the inspiration. Inspiration came from the green leaf. And I remember George Porter was also a big fan of photosynthesis. And he worked here at Imperial College with James Flintstone. And so we all tried to make artificial leaf. And so how far did we get? Well, I'll tell you a little bit about this. And so that inspiration led to innovation. And so the dye-sensitized solar cell is actually a sensitized mesoscopic junction. It's a monolayer sensitized. We can use monolayer of dye or quantum dots. However, it's a single layer sensitized. And so the trouble with that concept is if you do it on a flat junction surface, then the current will be very, very low. So you have to get 1,000 times the surface enhancement without getting the back reaction 1,000 times that times. And so that this mesoscopic concept worked out, and against many critical and skeptical views at that time. And also the photoelectrochemical cells emerged. So they actually, the way the mesoscopic concept works there is very different from the dye-sensitized cells because in this case we are using materials where the carrier diffusion lengths are very, very, very small. In the dye-sensitized cells, you don't have any minority carriers. So it's mainly the recombination time and collection time. You'll see that later, but better. However, in these materials, where we use semiconductor as light absorber, we have minority carriers, and so we have to bring those to the surface to react with water, say, make hydrogen or oxygen. And so the issue with, for example, iron oxide is that the diffusion length is much smaller than light absorption length. And so if you use a compact iron oxide, or rust, if you like, put sunlight on, nothing will happen. Okay. However, if you do mass structuring, you will get currents out of the iron oxide because now the base structuring allows you to capture these particles. So that was the different concept. However, it works. It works to your advantage. And so we'll be seeing also the what people call the second revolution, and so the advent of the health guides and also some applications. So as I said, in the dye-sensitized cell, you don't use a p-n junction. We have that's sensitized sensitizer as a monolayer between an electron select hole select contact. And so if we set that in motion as the injection process and as electroselective contacts, and you do work with the electron, you have to bring it back to the dye. So you need some shuttle that brings it could be a whole conductor or a redox couple. And so there's a solid phase version and liquid version of dye-sensitized cell. Yeah, and so going to this concept of which very tempting. It's very tempting to use that just very simple concept to have a dye monolayer, electron selective, hole selective materials, this sandwich in between, and many advantages. I mentioned some of those. However, there are also major caveats. And one of the main caveats is you don't get the light absorbed monolayer. And also, I mean, if you use a compact monolayer, a compact layer to a selective charge fraction layer, then you will have to dope it. Otherwise, it's not conducting the charge. So the dopants very often interfere with light absorption, quench the excited state. So anyway, the our if you like, our guru was actually got it good enough when he was in Oxford, and he visited us at that time to report on the sensitization of TiO2. Everybody in those days tried to get the light response TiO2 moved in a visible. There are thousands of papers on this that happens. And so John was trying this carboxyl complex. He was one of the few people that had really a monolayer. The others, I mean, they piled dye on an oxide and they didn't really know what they had. But John had made those chemical efforts to get the carboxyl attaching group. But you can see that at the end, I mean, the constant coming out in the nanoamp range. And so just compare this to 40 milliamps silicon photovoltaic cells. They're 6 orders of magnitude off what you need, a factor of 1,000,000. And so when I was a young postdoc, people said I shouldn't touch the area. It's hopeless. Okay, and for that very reason I just explained. And however, I had invited John Goodenough to Lausanne, and at that time he was very interested in our studies on colloidal semiconductors. This, I have to tell you, this was completely curiosity-driven. We were the first to make those colloidal solutions, and we realized we could excite the small particles. The laser, the solution looks transparent, and so you can do electrochemistry on the nanoscale using a laser to produce carriers. Okay, that was so years passed before we also sensitized these colloidal dispersions, and so you see here a paper, and but finally, I have to cut it short because otherwise 30 minutes would be on the history of that. Finally, what we ended up with was instead of using colloidal solution, we piled up the colloid on a conducting glass plate and sensitized it by carboxylate ruthenium complex. That was an idea that Goodenough had pioneered. And so, yeah, you can see if you now compare this, I should tell you that the colloidal particles, they have mainly a 101 surface facets. So we made a single crystal CI2 with a 101 facet exposed and sensitized it. And you can see here the current, 0.012 milliamps. So that's 12 microamps per centimeter. Better than what people got before, okay, but not impressive. Instead, you now use this colloidal, this scopic layer, we get 14 milliamps, so you have a factor 1,000 more current out. And that was an amazing phenomena that it's quite to understand it. Not only to understand, but to have the other people believe in it, because a lot of people thought that we had made a mistake, and we openly questioned on this finding. However, it was the truth, and I like to bring us before James to research. Yeah, because the reason, first of all, the question is how to get the charge separated. It's an interfacial reaction, and so electron can go in but come out of the TI to recombine with a dye. And what the studies that he published with James, like almost like 30 or more years ago, showed that there was a large difference. Injection, this is actually the same complex. I just showed you, measured the count-on. Same routine complex. The reaction is over in a couple of picoseconds, okay? And you can see most of it actually in the femtosecond range. But then the recombination of the electron with the dye, so the recapturing of the electron by the oxide side, is many orders of magnitude. You're talking here milliseconds, okay? The micro to milliseconds. So you have 8 orders of magnitude. And what that tells you is that the dye, it's a very simple calculation, shows you can take the dye over these many, many turnovers that you have together when you have dyed the sun for 20 years. It's about 100 million. And so that was a key feature, kinetic feature, which was then followed up by measurements on transport and recombination. And so, so what that's another critical. You inject electrons, you regenerate the dye. However, and what happens to these charges? They still can recombine and across the interface. And so how fast is the recombination transport? So that can be measured by impedance spectroscopy. And one bit would help as a great deal to model this with the transmission line. So we can get these 2 lifetimes of resistances out easily from impedance studies. And so what turns out is if I properly assign the dye molecule, the transport can be made 100 times faster than recombination. And so you collect your failures. I'll show you one example later. And so let me move on. So the Nature paper was published in '91. And then there's a picture with Brian, who was here also at Imperial College for a while. And he's now back in California. He was a postdoc with me, or master student rather. He did his doctoral thesis after it. And so now today we have these donor acceptor dyes, and I like to give credit to Anders Scharkfeld and Marina Freitag. They kind of minimize the losses in the regeneration reaction, redox electrolytes, and so that today, I mean, with these sense tests, we can get 15% solar to electric conversion. And one very important step was here you see the donor, chromophore acceptor, vectorial electron transfer. You excite the dye, the electrons flow from top to bottom. They are injected. The hole remains outside on the dye. So that makes very long lifetimes, and you get very high IPCs, very high EQE values, and so close to 90%. And now when you look at the lifetime of the chaos, they're over 1 second. And diffusion at time 120 micrometer. It's like a silicon photovoltaic. However, you achieve that with a much smaller dye quantity and much cheaper materials. And so, so these are today's mixed systems. And so we have gone up mainly by doing a lot of basic research to understand what's going on in these assemblies, and by working on the redox couple, the solid state system. And so, research is continuing in this field. Let's go on to the perovskites. Yeah, so perovskites, we have heard already a lecture this afternoon. These are interesting solids, they're ionic solids, and they have very strong absorption, allowed transitions. They have a band structure where the valence and conduction band are non-bonding orbitals, so that's unusual. The band gap has very few defects. And so that makes them really nice materials for photovoltaics. And so they evolved from dye-sensitized cells with the first study by Miyazaki, who just used the quantum dots of the perovskite methyl ammonium iodide, methyl ammonium lead iodide. That was the first paper published, and but very unstable, these materials. And so they dissolved in electrolytes. So for a while, nothing happened. Nothing happened. And only 3 years later, the studies were published almost simultaneously on a solid state version of the Dyson stress cell. And yeah, so this solid state version was building on Udo Bach's paper we published in Nature together, where we had replaced the electrolyte with this solid state Hall conductor, which is called spirometad. It's now widely used. It still is the best Hall conductor for perovskite solar cells. So many years later. And so, yeah, and so then 2 papers were published at the same time in 2012. And from there on, the solid state version became prevalent. And the rank prize was given last year to the folks that were involved on these papers. Many authors did all these papers, the 2 papers I showed to you. And yeah, and we developed it as sequential deposition, which means we solution processing. A lot of people just put all the components in a solvent and they print the paste or the solution and heat it, and that gives you perovskite. However, we found it was very interesting just to use the first lead iodide and convert it. And so that is actually now for us giving the highest efficiency. I'll show you that efficiency figure later. And so we're going back to a 2-step sequential method to get the top efficiency cell close to 26%. And so, but yeah, the focus of today, now let's talk a little bit about today's research, stabilizing the alpha former meridinium phase. And clearly that's optoelectronically the best, most attractive material. However, it's unstable. It has to heat it up to 150 degrees to get a stable alpha form, and it forms a very nasty material room temperature called the delta yellow form. And that's actually very much unwanted because it quenches the electron hole pair, and has all sorts of unflattened side effects. So you don't want the delta phase, you want this. But however, at low temperature, the delta phase is thermodynamically stable. So how do you get the alpha phase to stabilize? So one way is to just mix it the methyl ammonium with former meridinium. That was our first paper, and so that was still, I mean, today a lot of highly efficient perovskites use that mixture. Methyl ammonium stabilizes the former meridinium. Or if you use the cesium, you can also stabilize it. So you have here you have the two delta forms of former meridinium and cesium. When you grind them up, they return black, and you get the mixed stable black form. There was a kind of inflation in the alpha with the A cations. The triple A cation material that is now become the standard for the PIN structure. The PIN is a architecture where the light comes in through the P contact, and so yeah, and so now today, yeah, let me we are up here at 25.8, I guess now. And the configuration that achieves those high efficiencies are all based on tin oxide FTO. That's a quantum dot tin oxide. We're still using a mesoscopic contact. It's a very thin layer of quantum dot tin oxide, and yeah, and the spiral as a whole conductor. And so here's a paper published in Science a couple of years ago, I guess, and it shows you can get very good efficiencies. And electroluminescence also can be seen. External quantum efficiency is over 12%. It's very impressive to get those light emission also from the photovoltaic cell. It shows you have very little electron hole accumulation that is non-radiative. And so, However, here comes the crux. We have a problem with stability. I mean, slides are taken over 1,000 hours, and really you should not see any decline. And you do see. You see, it's maybe only 5 or 10%, but that's already too much. Okay. You want a 25-year-old T80 time? So T80, 25 years. Well, you can make a linear extrapolation. You didn't see any decay on this time scale. And so, yeah, so now the hunt for higher efficiency, I think, is pretty much over because people say, well, let's first stabilize what we have and see whether we can apply those highly efficient materials. And so also we need to scale up the module size. Most of these efficiency values are measured with tiny little clumps, less than 0.1 centimeter square device size. So if you go to 1 centimeter square, you already get a beating. The efficiency will go down, maybe from 25 or 26% to 24%. But we have to be honest and say this has to be addressed, and we have to be able to make mini modules and modules that can compete with silicon. And that means they have to reach a 20% efficiency on the module side, 30 by 30 module. Is it possible? I think so. However, you're not there yet. You have to work on it. And so, yeah, so here is, as Skip said, we have the problem with iodine decomposition. And here's here's a paper I want to draw your attention to. It was published this year in January. It's a joint paper with the group in Wuhan. Xiong Li is a former postdoc. He's now a professor at Huazhong University of Science and Technology in Wuhan. And we worked for 2 years to get that paper done. It was not something that a couple of weeks you could write a science paper. And so we had corroborative effect investigated this C60 derivative as a material that would enhance, that would be on the grain boundaries and improve cohesion of the grains and enhance electron flow across the grain boundaries. And we also did a doping of the spiral with the redox active polymer, it's a tempo derivative. And so outcomes a cell that, let me see, the module is more efficient. The module is over 21%, and the single cell, 1 centimeter cell, over 23. That's very good. We are very happy about that. And so so now the efficiency, the stability of this, I show you that as a final slide. I show you the stability, and then a few minutes about applications. And so you see today these systems have 3,000 hours and less than 5%. That's at 70 degrees maximum power point tracking. And so that's a challenging condition. You keep your cell on the maximum power point, full sunlight for 3,300 hours, and that's about half a year or at least 4 months. And then keep temperature up, combined heat and light stress, and you get less than 5%. That looks good. So we can think about scaling this up and putting it outside in the sun. So now, just to relax you, some applications, mainly in the DSC field. So the scale-up, the carbon cells, we have to replace gold by carbon, so carbon cells will become very important. There's a group here at Cambridge that has developed some kind of a paste that is made out of from graphite. They grind it up and has graphene particles, and it's supported by a bunch of research. So this is a spin-off from the Andrea Ferrari's group and our group, and so financed by a bunch of IP. That's a UK Cambridge. I think it's a venture capitalist. And so I'm involved in Turkey, setting up a production line of perovskites there. And we will use that carbon for this production line, this product. Yeah, the Dyson test now finding applications mainly in these vertical glazings. This is a car charging station in Switzerland, and our facade. And I'm very proud of this picture we had at the Milano World Exhibition. They had this big wheel. These are all Dyson Stress systems. There was a forest behind it. That's the Austrian pavilion. And so my wife and I got invited to. It was on the 11th of May, and we both have our birthday on the 11th of May. So I got a birthday cake from them. And this here is this is the car charging station, 15 kilowatt peak. Not bad for a Dyson system. We used to give nanoamps a photopower. Okay, so the forecast has to be good. And this is a truck that's been charged by those panels, and it serves to forest. And so lots of outdoor testing, and also now the ambient light applications are very prominent. And so I just show you this year, there's Ambient Photonics in California has set up a production plant for DSC and ambient light harvesting. This is a Swedish company in Stockholm, first factory. That was like in 2014. And King was there, and Giovanni Fini, the CEO, and Henrik Lundström, he's the CTO of the company. And here are the first products. These are the Dyson styles, solar cell flexible, and you can buy eBay, you can buy those earphones and the bicycle helmets. They're all powered by light. You don't need a battery. You don't need to worry about whether your battery is empty or full. Okay, which is a big advantage. And so companies like Adidas and Ubista are commercializing. And I have one 30 seconds. That's the Exeter company that produces those. And you can see this is really serious production, 1.5 million square meter a year of this powerful. So it's a serious application, and other companies are doing it. However, I think that Extra is a leader. They have already set up, or 2.5 million. They set up their second production plant because it's an application that is very much under demand, and so they found a niche, in other words. Okay, well, with that, I'm finished. I just like to thank my co-worker. Very important to ski in Switzerland. So if you want to become a postdoc with us, you have to take a skiing course. Okay, and I show you, I'm myself still skiing a lot, and so still on black slopes. And so, however, we are getting this beautiful panorama. And so with that, I finished. Thank you for your attention.
Thank you so much for the impressive presentation and for showing all the path that you follow to achieve these amazing breakthroughs and impact. So now we'll pass to the panel discussion where we can ask questions on the presentation and on different topics. So maybe if you want to sit.
Sure.
Yeah. And I also invite Anna also to join us. So we have here some questions for you.
Sure.
And we also ask the audience to ask questions. Yeah.
Just to make your camera. The presentation and online as well. If you have questions, you can post them on the.
All right, Michael, thanks very much for accepting our invitation. Firstly, it's a pleasure for us to meet you here, and hopefully this will be the start of a wonderful collaboration with us. The question I have is about what you called curiosity-driven research. I think you made that comment at one point during your presentation. And my question is, to what extent was all this kind of curiosity-driven, and would this kind of work be replicable nowadays in the current climate? What do you think?
Yeah, I once gave an interview to a journal called The Spectrum. I don't know whether you know that. It's from Bowling Hill, Bowling Berlin held a photochemical university in the US. And if you're interested, I can send you a PDF of that interview, where they asked me all sorts of soul-searching questions about it, how to invent something. And so, yeah, so how one question, how did you invent the dye-sensitized solar cell? The answer is, I mean, these are very often serendipitous things. You have to, when somebody does research, he does it out of curiosity, I hope. Not because he wants to get rich or he wants to invent something. He wakes up one day, I want to invent a solar cell. That's not how things happen. And at the time when we were starting, we were really interested, and still are, mainly in the solar fuels. We want to make hydrogen from sunlight. And James knows that. We have this famous IPS conference that goes around the world. And I don't know which number we have now, maybe 25. It's like 50 years old every 2 years. So, yeah, so at that time, we were all trying to make hydrogen from sunlight and water. And Ti2 was the preferred material because Fujiwara and Honda had published that paper. And so, however, the UV response, and so there was a big motivation to try to use sensitization to move that response in the visible. So that was actually our first motivation to move in. However, we had been interested in a colloidal state of matter for a long time. We worked on micelles and vesicles, and we had done photo-driven electron reactions, transfer reaction micelles. So it was natural to go to inorganic colloids. And so that was, so it's curiosity driven. We just wanted to explore something that was unknown. And with colloidal state, we were able to get a more detailed picture in this charge transfer reaction. And I mentioned James' work. He has done a lot of this in the last few decades and contribute a lot to the understanding how does the water splitting happen on the colloidal Ti2 particle. And James found out how these holes are accumulated on the surface. And so we need to go first to the bottom, understand. Then you can say, oh, maybe we can use those as an array and try to make a solar cell out of it. And so however, I mean, this has taken many years, and that's why I'm a very staunch defender of fundamental research.
Thank you.
So we have some questions online. So I'll read the first one from Aaron Walsh in Materials. So very interesting talk, Michael. You emphasize the importance of stability. Many routes appear to engineer kinetic stability, but are these sufficient for expected device lifetimes of several decades?
Yeah, I mean, you're getting there, I would say. When we started in the postcard 10 years ago, this was a completely open question. And however, I have to say that we had done very early on a heat exposure test. And I asked one of my postdocs he was from Saudi Arabia. I said, you should put some in the desert and have the sun hit for a while. But since he was with us, I said, let's first use our oven and put the cell at 90 degrees and wait, say, 1,000 hours, see what happens. And nothing had happened. The cell was still okay. And he forgot actually to take it out. So after two periods of 1,000 degrees, it still was okay. We published that. And so it showed the thermal stability was not bad at all. It was thermal stability. Now, what you have to do is you have to apply both heat and light stress. And so that's a real critical test for perovskites. So we have these so-called ISOS protocols now. There's an L3 test, but I recommend very warmly to those of you who work with perovskites read that paper. Nature Energy. It tells you all the tests. The community has accepted those conditions. Even the funding agencies have. And so today, L3 means you have to have around 70 or 75 or 80 degree long at least 1,000 hours maximum power point tracking. And then we talk, what is the T80 type? And so we have to go to the bottom of the truth. It's not, I once had a postdoc who said, I carried out at room temperature. I said, why didn't you go to 75? Oh, it's not as pretty. I said, stop. Science is about facts. And so we have to have the facts, hard facts. And so far, I would say the odds are in favor of having a long-term stable material.
Thank you. Any question from the audience?
Thank you very much for the talk. I'll go back to the carbon question. You mentioned the need for changing gold to carbon and for commercialization. And I just wanted to ask, how do you see this process? Do you see any fundamental changes needed to be done for perovskites, or is it just a simple engineering question?
Carbon is a real blessing for perovskites. I mean, it's much better than any of those metals, because the metals corrode iodide, even gold corrodes with iodide. And so don't forget that the metal contact is under polarization. It has a positive potential on it. So that helps the oxidation of the gold. And whatever you have as a metal, copper is worse, silver is worse. So these metals are out of question, because there is no way you can avoid some of the iodide to creep up. And so in outdoor testing, all this corrosion has been the main reason for rapid decline. And so, but carbon, the perovskite loves carbon, and vice versa. Okay, so that means that even if you just have no hole conductor between the perovskite and the carbon, that was, I think, yourself, and then it still was running. And I guess the reason why you saw the decline, that was not this contact that was problematic, because the Wuhan cell is, we have published in a science paper with Hongwei Han, who is the center director there. And this run was very stable. We have a module that ran for a year under full sunlight, published in Nature Communications, and there was hardly any change. So, and don't forget, in a Z-type connected module, you will have direct contact between the carbon and the perovskite, whether you like it or not, because the P2 writing, okay, creates this this contact. And however, it's of course as well only a small part of the surface of the perovskite is exposed to carbon, but there is exposure, and so that hasn't done any harm. Okay. And I mean, if there was a harm, Hans cell would have died immediately because he has full contact. However, if you have only carbon, no selective contact, it costs you voltage because it's not a carrier selective contact.
Hi. Well, first of all, of course, thank you for it was an impressive talk. And my question is regarding the field of solar cells, because I don't have a solar cell background, but I think pretty much everyone that works in electrochemistry or photoelectrochemistry is aware of all the progress and the boom of solar cells. And it feels like since the big boom of the solar cells, like all the groups that were working on dye sensitized sort of shift a bit to quantum dot sensitized solar cells, and then all those groups as well towards perovskites. And then perovskites has a lot of place to, like, I guess, to expand, because like there's a lot of different combinations with the cation and everything. But how do you see the field going forward? Do you think that will shift again towards some sort of different configuration, or what are your thoughts?
Well, the dye sensitized have now been commercialized, and so we're getting money from industry.
Yeah, of course. Yeah, I mean.
So I wish there were more people. All my DSC coworkers were hired by a company, a local company. From one day to the next, I lost all my stuff, and so I would welcome a synthetic chemist or somebody who knows the device, we will rehire people in a DSC because we just have a lot of questions coming up now from the end users. However, we also develop new dyes. I have some new ideas, and so that will make it more powerful. And so that race is not over.
So you think that in academic research, then there should.
However, I think the applications of dye-sensitized cells will be very much in that area where we have, on the one hand, these modules, the glass modules. Vertical positioning gives us a competitive advantage over silicon because we can collect bifacially the light, albedo, and so now is now a site being built in France, in the Elf Aquitaine. I'm going to Bordeaux and next week, I guess, or a couple of weeks, to discuss with the president of the region. And so commercialization of these glass panels going on, and you have seen they play these outdoor ambient light harvesting. There are already products out there, and so we should support this development because it saves battery power, and with the photovoltaics, we just need to have different technology. We have to increase a factor of 200 the photovoltaic output in the next 30 years to meet the Paris Agreement. So disaster is on the horizon if we can't. So we have to use any technology. We should not reject that can be competitive, and I think the single junction and tandem PV cells, the tandem cell with silicon perovskite reaches now 33.2% efficiency. That's impressive on a 1 centimeter squared size. So that's the highest efficiency of double junction cells. Even gallium arsenide silicon cannot reach that. And so we have to, that's why, I mean, all these exciting new discoveries. And so hopefully it will attract lots of gifted and motivated young researchers. And so that's what we're counting on. And yeah, so and then there comes the solar fuels, also very, very important, because electricity has a caveat. I mean, it's not always there. Okay. So we have to store electricity. And I think the direct way is just to use electric power to electrolyze CO2. We can discuss that in more detail later. In my opinion, I've got a contract from industry to make water gas out of CO2. Okay. Why is that? Well, because water gas has more value than hydrogen. Okay. And so CO2 has a negative value. So they do their own commercial calculations. And they tell you, I want water gas with this kind of ratio between hydrogen and CO. And so we have published a paper on 20% solar to CO conversion. However, this was with an expensive triple junction cell. So now we have to go to the perovskite double junction that gave similarly high voltages. I mean, it's kind of this is kind of an engineering task. Okay? We are scientists. We have to make sure that we understand everything, the fundamental truth about this material, and they are complex, and they're highly complex, and many variations, and so it will take time.
Thank you so much.
So we have, I think, one last question from online, and then we can open it to Anna and Salva. So question from the online attendees, from Simon O'Kane. What is the expected lifetime of commercial perovskite solar cell devices, and how does this compare with more established technologies such as silicon-based ones?
Yeah, that's a good question. What is the lifetime? Well, I know for silicon how much the T80 time is. They claim 25 years, or say 20 years. That's a T80. Doesn't mean they are stable. They have lost 20%, okay, during that time. And so at the end, you have less than I have silicon panels. I make my own measurements on my chalet in the mountains. And so yeah, so can we beat that? I think the perovskite, the single junction with a carbon, I think so. I mean, we have gone through these thousands of hours, and that's not the end of it. We can still improve. And so, so research is, however, we at this time have to be careful not to overstate our case. And we have to tell the investors to be patient and wait until they can invest. However, there's a risk in any of those technologies. And however, we should not overstate our case or oversell. And the science should be always pragmatic. These are the facts. And the facts are today, if I take the d80 of our test, it has to be done on a small cell, okay? And maybe already 50 years. If we do the 70-degree correction, you usually say a factor of 5 anyway. If you do, say, a 30-degree test, since you're running all the time. However, there's also the temperature cycling you have to test. And so all these experiments are being done, and I'm sure that we had a lot of progress. And as I said, I'm optimistic now. I was less 5 years ago.
Yeah, well, I don't have a mic. Yeah, I wanted to ask, probably you've got this question before. What about the lead cations presence? Is this something to worry, or are there ways to encapsulate it or absorb it with MOFs or others? What's your opinion on this?
Yeah, that's a very good question. I had one slide. Unfortunately, I wasn't able to comment on it. We have to be very careful with the lead. And so this will restrict, in my opinion, and I think I'm not the only one, the applications of postcard solar cells to solar farming. It's like telluride. Cadmium telluride has this application. They're doing well. They have over 1 gigawatt installed, and First Solar is happily making profit. So, however, some people, they have illusions about using flexible devices or consumer products like the ambient light applications. That you can forget about. I mean, and we had the Nobel Symposium a few weeks ago in Jenny Nelson was there. Anybody else was there? So she can tell you more about it. However, I flagged this slide up, which shows the ROHS, restriction of hazardous substances, rules regulations in Europe. And so the regulation is 0.1% lead in your active. So if you take the lead particle, it's 30%. There's no question that. However, there's the exception. The exception is if you have it in firmly installed panels, you can use higher percentage. However, if you sell products, consumer products, that's not the case. You violate the rules. You may go to jail for that. So better not raise false expectations there. However, I mean, solar farming is fine. You can make plenty of electric energy with solar farming.
On the subject of solar fuels, we wanted to ask about some of the work that you've showed where you made not solar cells, but semiconductors for having a semiconductor liquid interface in an integrated photoelectrochemical device. Now, progress on that has slowed down a little bit when it comes to complete devices with fully integrated electrodes. What do you personally think about that route still versus the PV plus electrolysis separately?
It's a very nice system. I love it. I mean, we're working on the combination of cuprous oxide as a photocathode for hydrogen. Now we can even make formate on the cuprous oxide, and we have. I could show you the slide. It's very simple. You have a cell where bismuth vanadate is the first. Say it's the anode, and the light comes in through the anode. And then we have just a wire connecting to another glass plate, which has the copper on it, copper oxide. So it's 2 glass plates, and you can make hydrogen oxygen with over 5% now. This is very simple. It's a poor man's photoelectrolyzer. Okay, no, it's really. And if we get a better photoanode, I mean, bismuth vanadate has its own problems. And somebody said 5 milliamps. We're getting 5 milliamps per square centimeter. So that will limit the efficiency to 6%. Or we're already very close to the limit. Okay, and so we need to work. We're going back to the photoanode. We have to make a better photoanode, and
Between cuprous oxide and the
Cooper's,
bismuth vanadate, you find that the bismuth vanadate is the least stable.
yeah, absolutely. Because the cuprous oxide we can now put on a silicon support, and we get actually 1.6 volts out of this junction. So you have a double junction, silicon with a cuprous oxide with gallium oxide. And that gives you 1.6. You don't need any other voltage. You could use that as a photoelectrolyzer. And so, however, I really like that experiment with the two glass plates. It shows you the power of the photoelectrochemistry. And by all means, we should continue working on that. Who would have thought that we get to these kind of values, say 10 years ago?
Thank you.
So I also have more questions. So you have had a chance to supervise and mentor many scientists. In your opinion, what does it take today to build a successful career in academia, and how has it changed over time?
Okay. Well, I mean, first of all, somebody who wants to do research, he should be motivated and passionate about what he's doing. And I never had a lack of motivation. And so we all are motivated, and you should do that what you're really passionate about. And then be careful when you do experiments, to be careful not to miss to distinguish the unusual from the just standard average. So you have to train your eyes and also you have to be educated, because if you don't know what the standard is, like when we start our Dyson stress cell work, we had first some kind of a fractal electrode, which was not this particle electrode, and it was a high surface aerosol JLTI2 film. And it was given to us by a colleague from Geneva, who used it for completely different a catalyst kind of application. And so I asked my student to do a dye sensitization. And so Jean de Silvestro came back and said, well, the counts are still low. It's a few microamps. I said, the others measure nanoamps. So once you see a trend like that, you have to follow up on it. Otherwise, somebody else will perhaps pick it up. So you have to read also what the literature says, and so you don't have illusions what you're doing, and you can relate your studies to what is known. That's very, very important.
Thank you. And how have you seen the academic career changing over time? Is it still the same than some years ago?
I think it's actually easier. It's easier nowadays to make an academic career. I tell you why. Most of the universities in Europe, at least, when I was a young scientist, we had to go through this habilitation. We were absolute slaves of the professors. Okay, we had to call them professor, and so if you were crossed with your professor, well, you were done. Okay, and so all this has dramatically changed, and we have to thank our American colleagues who put a lot of flexibility and competitiveness in the science, and maybe in England too. I'm less familiar with the English system, and so anyway, this whole scenario is now we have the young professors, the assistant professors, tenure track, they're all tenure track in Lausanne, And we do our best to help them. So it's not that somebody stands with a whip and wants to squeeze out data and then publish it in his name what other people have done. That's not happening anymore. So I would say it's a field that's more dynamic, has opened up, and young people get much more support, and excellency matters. And you have the ERC grants. I myself, I'm at the ERC panel chair, and I make sure that the excellency is. The panel chair has a lot of clout at the ERC, so I make sure that excellency counts and nothing else.
Thank you. And where do you take the most pride in your work?
Right. Huh. Well, I think I always was interested in natural photosynthesis. Okay, that was actually why I studied chemistry, because I thought I would better understand, and I think that's correct, that you need to be a chemist or a physical chemist to understand all the intricacies of natural photosynthesis. And I'm very proud that in a way we were able at least to mimic the light reaction, which is photo-induced charge separation using a molecular sensitizer. You can do more. You can couple it with the with redox reaction. This has been done. However, the nature has found a way to solve that molecular problem I told you. The very outset, nature had the same problem. How do you manage the sensitized heterojunction with a monolayer of sensitizer? So the first thing they have some light harvesting complex. So, however, at the end, the dye has a monolayer, so-called the photosystem 2. It's a dimer, it's called the dimer. So how does light get absorbed? Well, it's the trilobate membranes are stacked. It's like having these colloidal particles that are stacked. In a way, we use a very similar trick that nature uses.
Interesting. And yeah, I wanted to ask, what is the most effective way to convince governments and policymakers to integrate and extend the use of these novel technologies and avoid fossil fuels? Because often I see amazing breakthroughs, but they struggle to reach the commercialization because of policymaking, I think.
Do you have a problem like that here in the UK? I thought you don't.
I think we all
You do? Because
we see, for example, subsidies to fossil fuels are still higher all around the world than to renewables.
I see. Yeah. Well, I mean, in Switzerland, the Green Party has become, also I think in Europe, the Green parties have a lot of clout now. And so you have to go out and talk to the people, make noise. And like I'm in a consult, we're trying to avoid some trees to be cut down for no good reasons. So in Switzerland, we can't go for a referendum. We will launch it. We will go to the federal court. So you have to be determined to, and then you will see the followers will come. And there's a policy, but I remember that we had these sessions with the advisor to the Prime Minister here in the UK. I forgot his name.
The Prime Minister or the advisor?
The science advisor. Yeah, David King. I mean, David King played a very good role, I thought.
But he's no longer the Prime Minister.
Well, please appoint him. Try to get somebody else that because I met David King and I thought that he was very good. And we set up actually a company, Hydrogen Solar here, and it still is alive actually. Yes. But I'm not anymore involved in the management.
Thank you very much.
So we imagine that, like many academics, you will have had some ups and downs in terms of running the research group over the years. So we wondered, based on your experience and observations, what is required to run a research group as smoothly as possible?
Yeah, well, first thing I would say is be open, be transparent, support your people. And if there is a problem, it should be broadly discussed. We have meetings, group meetings, every other week. We take a break and say, hey, let's see if there are any problems pop up, like moving the lab or cleaning, and so we have to also make people responsible. So dividing tasks, rewarding the people that help the group, and so I don't think a dictatorial system is as efficient as a system where you let everybody evolve to the maximum performance it can instead of suppressing activities.
Mm-hmm.
So yeah, it takes maybe more time, and we sometimes have issues with the names on papers. Okay, who is first and who is second, and who gets a star and doesn't, things like that. However, I mean, I always will then, everybody who is involved will be called, and we meet, and then we can't find a consensus. We will call another judge in, and it listens. And so that takes time. However, that's how democracy works.
So independent advice on authorship helps solve the problem sometimes.
Yeah, I mean, we have very strict rules at the EPFL about who should be on a paper or not. And these should be firstly followed. They are very good rules.
Mm-hmm.
They are thought through. And so that's the first thing. And the next thing is who did what, and that we have to value. And we also I have the possibility to give small awards out. So every year it's something like a £3,000 award. Okay, somebody who, so I can propose to the dean, and he will usually follow my propositions. And so, and then we discuss why he got the award and so on. Everything has to be transparent. Takes the time, it will pay off.
Following on from that, we often discuss, at least lately, how much an academic career takes out of academics and researchers, and that it's quite a struggle to maintain a reasonable work-life balance over a prolonged period of time. How have you managed over the years?
Well, I mean, yes, you're absolutely right. I mean, there are days when you get really in a sour mood and nothing seems to work, and well, then your motivation has to kick in.
Mm-hmm.
Okay, and hey, that's normal. That's completely normal. They don't get depressed, and so yeah. And so I always have taken a positive attitude. Okay, and trying to solve a problem instead of envisaging problems to come. There are people that see all sorts of problems on the horizon. I never do that. I deal with a problem when it happens and try to solve it in a positive way.
Mm-hmm.
And so being optimistic is I think not a bad attitude. And so yeah, of course, if somebody wants to get rich, and that's his goal, he shouldn't go into science. And he may get rich, some scientists do. However, that's not a straight path. Okay, if you're a banker, you may have a better chance. But you could also get very poor as a banker, so be very careful. And so yeah, so.
That's also a discussion we have quite a lot, especially when it comes to undergraduate students and why they leave.
Yes. Some of my doctoral students, they went, with Swiss, we have quite a lot of banking jobs, and or with companies that are consulting companies, but that's fine. I mean, you know better what you want. You can always change if you think you made the wrong choice.
Well, that's it.
Yeah.
Okay.
You can.
Yeah. So thank you so much. It has been very interesting. I think for the sake of time, you should leave it here. But yeah, you have now one-to-one meetings around, so we'll have more time for discussion. So let's thank again Professor Michael Graetzel. Thank you very much.